These kind of enabling technologies for 6G would be AI or machine learning, millimeter wave and sub-terahertz bands. There's research going on in that. Reconfigurable intelligent surfaces. This is kind of like a new node in the network that is supposed to act as increasing the coverage or doing some kind of passive beamforming around corners and so on. Non-terrestrial networks, I already said this is becoming really important, providing cellular services over satellite or ad hoc on-demand services from satellites. Cell-free massive MIMO, other things. There could be other things that come up between here and 2030 when the standard actually comes out. So we are aligning our tools to be able to provide ways for people to use this. And in response to that, we have shipped out the 6G exploration library, which is just an add-on to the 5G toolbox. You can just download it if you have the 5G toolbox. It, just like the 5G toolbox, has got the full MATLAB source code, and it allows you to explore options far beyond the 5G standard. So if 3GPP said you can only do bandwidth up to 500 megahertz, we've removed that. You can do bandwidth up to 1 gig, 2 gig, if you wanted to, or subcarrier spacing up to 1 meg or something like this. So that's on the waveform side, and then there's more. So if I show you what that is like, if we go to the 5G toolbox. So first of all, how do you install it? Let's talk about that for a second. If you have the 5G toolbox, you can just go to add-ons, get add-ons for 6G. You will find 6G exploration library for 5G toolbox. So that way you can just install it. You can do is you can also look at the documentation and the various examples. So you can see here that we are allowing you to go much beyond what the current standard allows you to do with the subcarrier spacing, with the resource grid, and with something like 4096 QAM. So beyond 1024 currently is what is supported. They're looking into beyond 1024, so 4096 QAM. I think this is already used in WLAN 802.11b, if I'm not mistaken. You can start exploring that and use that to test equipment, for example. In the same manner, we have that same link level simulation, but this time going beyond what the standard permits, looking at things like sub-terahertz on 6G waveforms, modeling RIS, reconfigurable intelligent surfaces, as cluster delay line model channels, performance of cell-free massive MIMO networks. So in addition to that, there are also some AI example implementations we've put in on leveraging AI inside of the physical layer, either whether it's auto-encoding or positioning accuracy, using AI for positioning accuracy. I think I got asked about was the OTFS. That's another potential candidate for the 6G standard. And the reason for that is because OFDM can suffer from high inter-carrier interference when it's in a high Doppler multipath channel, but the OTFS is different because a delayed Doppler domain is used. So it's a new candidate that they're looking at for specific environments like high-speed mobile environments. May be useful for non-terrestrial networks as well with the high Doppler situation over with LEO satellite. We have a getting started example on that too, that you can start making some of these waveforms. Have I missed something? I've talked a lot about 6G. On the simulation, going beyond the physical layer, we also have a network simulator, which is growing in capability and in scope. It allows you to simulate different things. For example, various topologies depending on the standard you care about. For example, mesh networks, hybrid mesh, this is more like WLAN terminology. This sort of hexagonal, this is cellular technology, and star networks as well. So depending on the standard you're simulating, you can do a bunch of things. Networks can be very small, just 2 neighboring cells maybe, and they have some, if it's a CDMA type technology, they can be interfering and kind of having contention for the access to the channel. It could be something like a cellular topology with a number of UEs, or it could be a network where we have both on a shared band, like with WLAN, with Wi-Fi and Bluetooth, having to contend with the network, and Bluetooth having to do hopping around the WLAN, for example. So looking at things like coexistence there. The wireless network simulation library is, again, also an add-on that you can download on top of the communications toolbox. If you look at the add-on library again, we go to wireless network, communications toolbox, wireless network simulation library. There it is, and you can install it. This one I do actually have installed, which is good. What's interesting about this one is that it's also MATLAB object-oriented type of the way it's been built, let's say, and you have a wireless network simulator which runs the whole show. It has various actions you can do on it, like you can add a channel model, adding nodes, removing nodes, running the network, canceling what you're doing, and scheduling some actions during a specific time in the simulation. You have various nodes which are representing cellular nodes or WLAN or Bluetooth nodes. So mix and matching them, it depends on what you want to do. So you can put together WLAN and Bluetooth, but cellular and WLAN, for example, is not yet supported. It all depends on whether a specific band is even shared by these technologies or not. Traffic models, and then there's additional kind of internal things that pass information around. So the whole code is fully open, right? That's what I'm saying. So if you need to modify this, if you need to change the scheduling mechanism or something, there are methods to modify this to suit your needs. Like I said, it's all kind of object-oriented, It's class-based, so it is a wireless node. The other nodes derive from that, and so on. So you could, in theory, obviously derive your own type of node that you want and use it within the same infrastructure. It's usually needs a bit of support and help from us, or potentially involving our consulting services to do that. It becomes really useful is when you have to do the type of, again, Monte Carlo simulations for wireless networks. And what you can do is, once again, you can farm out full simulation with a different, for example, modulation carrier scheme or slightly different node configuration or something. You can farm these out in parallel and then get the results back. Things like throughput, there are statistics you get for the MAC layer, for the physical layer, and so on. So let's take a look at an example here, just so that it makes sense. I'm going to jump to WLAN just because we did a lot of 5G and LTE, but there's support for those too. The WLAN toolbox, simulation, examples. So there's quite a few, and they become some of them become more complex as they go. So on, including coexistence. So very simply, we configure our scenario by configuring the nodes, any other associations, they're already kind of associated, application traffic, the channel, we run it, we get the results. Very straightforward. Do we have the support package? Yes, we do. How long are we simulating for? 1 second, 10 seconds? How long? Do we want to see visualization? Do we want to see performance plots? Yes, we do. Now, there's implementation for both abstracted and full PHY. We've leveraged all of the standard compliant PHY level functions that we have to make actually a full PHY simulator. So the complexity and the fidelity can really go high here, but that also has an impact on the performance, right? So it'll take longer when real packets are being passed through the network. So we're not going to abstract the MAC, but we are going to abstract the physical layer. We can also choose to capture the specific packets to a PCAP file for further analysis. We're going to configure our scenario, our network simulator. It's our network simulator. It has a channel. We have a WLAN device config for our access point and our station. This is very simple. It's just 2 things. So you can see it has a lot of properties. Some of them are MAC specific, some of them are physical layer specific, but you see you have things like even BSS color, beacons, and so on. More importantly, channel bandwidth and transmission format. So whether that is a 802.11ax or BE node or what flavor is it. Then we have our actual WLAN node, which has its device configuration and whether it's MAC or PHY abstracted or not. And it has a position. So this position is just relative XYZ position in kind of an abstract space, if you like. We have associated our nodes, and we have defined our channel using TGAX channel model. That is one that is IEEE channel. We're going to add our nodes to our network simulator. And we have our nodes 1 by 2. We're going to add them to our network simulator. And then we're just going to run for the simulation time we wanted, which was, I think, 1 second. We've added some nice visualization here to see what is happening over time on the different bands, on the different, nodes in the network. We've color coded what is happening, whether you're transmitting or there's a contention or reception failure and so on and so forth. You can imagine here that as you add more nodes, the probability of contention will be higher and reception failure may fail as well. So this is a very simple example, just two nodes. Later on, what happens is we can look at our statistics, which there is a lot of them. We get statistics, one for the AP, one for the station for each node, and we get statistics for all layers. Application layer, if we go to Mac layer, I have a lot of statistics here. There's a whole documentation page that explains all the statistics you can capture, and I believe you can add your own custom statistics to that as well. Needs a bit of modification, but that's the basics, and then you keep building on that, the complexity of the examples. And they have been validated against some of the IEEE. There are some papers on specific scenarios and metrics that they've been validated against. I talked about non-terrestrial networks already. I talked about their importance. There is also now a channel for non-terrestrial networks that got defined as part of 3GPP, which uses what's called the LMS channel, Land Mobile Satellite channel, as the basis of it. So I won't go into details of the channel, but that channel, we have now an implementation of it. And so you can imagine now that if we have the 5G, we have all the components for 5G link on the transmit and the receive side. And now we have the really helpful non-terrestrial network channel that will more accurately represent the impact from the ground up to a satellite. We can now use that throughput example that we had, but actually replace the channel with an NTN channel model, and also model our Doppler pre-compensation and post-compensation due to the satellite movement. So the example I showed you earlier, it grows and is modified to work like this. So you have the dark orange stuff, which is the 5G. We already talked through that. We already talked through this. The satellite specific stuff comes in here. So there's some impairment by power amplifier. You can omit that if you don't want it, doesn't matter. But then you have the Doppler pre-compensation, the NTN channel model, and the timing is a little bit more complex here on the synchronization side. So this is now the analysis over satellite link with the NTN channel model. There's many other things I could have talked to, so I'll take some questions on that and I can bring things up as necessary. But just to conclude, I tried to build a picture of view of wireless communications today and where the main interests are and where we are investing our efforts to provide capabilities, including on the waveform generation side, the end-to-end link level, the satellite and how that satellite orbit propagation and how that fits back into the cellular scenarios, the coverage analysis, moving beyond 5G to 6G exploration, the non-terrestrial modeling. It I think became kind of obvious what we're doing here. It's just like the end-to-end. And then on the wireless network simulation as well. So going beyond the physical layer, going above into network topologies and looking at capacities and throughputs and things like that. In 1 hour or so, it's really hard, to just go through everything. We kind of scratching the surface, which is why I'm happy to take any questions on capabilities or things that you think are missing or how to do this, that, and the other. So with that, I'll go to the Q&A if that's all right.